as we continue through molecular orbital theory, I want to start out by just a quick review of where we were at. Just as a reminder, with what we're doing now, we've switched gears from hybrid orbital theory, which was a way of explaining shapes of molecules by taking the pure atomic wave functions of the central atom and combining them in such a way that when you put them together mathematically, by combining those wave functions, what you get out are hybrid atomic wave functions, which allow you to better predict the shapes of molecules that you get from, say, via CPR theory and a localized electron bonding model. We shifted gears here to talking about a little bit more about bonds and the overlap of orbitals within a molecule, which is molecular orbital theory. And so we've kind of diverted ourselves. We're going to actually come back and bring molecular orbital theory and hybrid orbital theory back together in a little bit. But molecular orbital theory is saying, hey, if you combine two orbitals now from bonded atoms, right? One orbital from each bonded atom, and you put those together, you get a bond. And that bond that we're modeling through the mathematical representation or the mathematical model that we consider wave functions. But if we put those two orbitals together, we're going to get these two molecular orbitals out. One of those will be a bonding orbital and one will be an anti-bonding orbital. And we're doing it so far such that we're only putting two orbitals in, right, for a single bond. We're going to get to a point where we're going to start to put in more orbitals in for, say, double and triple bonds. And again, we're taking orbitals from different atoms here, having the overlap of those orbitals, combining the wave functions to spit out these new molecular orbitals, and we're then populating that with the electrons from the original separated atoms in the first place to show the bonding in a molecule. And we're sticking with basically diatomic molecules for the most part, okay? And so far we've really only looked at one molecule, and that was the hydrogen molecule, the H2 molecule. And so the H2 molecule, we have essentially constructed a molecular orbital diagram for it, where we have, as you can see, so this is one of the old slides, we have representing a hydrogen atom, right? We have an energy, so the energy diagram or the energy axis, on one side of our molecular orbital diagram, we have one hydrogen atom represented. And of course, we have the valence orbital is the 1s orbital, and there's one electron in a hydrogen atom. On the other side, we have a second hydrogen atom. Of course, these are separated. These are before they bond, right? So these are pure atomic orbitals on the atoms that are separated. And the pure atomic orbitals, what's going on there? Did not mean to do that. So the pure atomic orbitals on the, my eraser, losing something. Okay, on the bonded atoms are you have the 1s orbital with one electron in there. And when those two atoms come together, you wind up getting a you wind up getting these hybrid atomic orbitals, the 1s, sigma 1s and sigma star 1s orbitals, and we take the two electrons, the one from each of the hydrogen atoms, and start to populate our hydrogen molecules orbitals with those atoms. Okay, so that's kind of a key here for what we're doing. Okay. Something to note as we've constructed these are when we look at the actual orbitals themselves, right, we look at the pictures of those orbitals as being, well, over here we've got our 1s orbital from one, and that's corresponding to this 1s orbital here, right? But it's a pictorial view of it. This other 1s orbital, that corresponds to this orbital here, again, a picture of it, and then we've got our molecular orbitals, right? This one here is our sigma 1s orbital, and that's the one that's represented there. And then we have our sigma star orbital up top, which is represented down here, okay? So, what's up with that? The next part to this is we're going to complete our MO diagrams that we started last time for the H2 plus molecule, which is just a hydrogen molecule that's lost an electron, and we're going to do the H2 minus. And so far what we've constructed here before the end of class last time was this, the molecular orbital diagram beginnings, which are the atomic orbitals within that molecular orbital diagram. And the first one that we have, so we'll do H2 plus. When we combine the orbitals for an H2 plus molecule, they're the same orbitals that would be combining for the hydrogen H2 molecule, except there's fewer electrons. And so what we get is when a 1s orbital from each of the hydrogens overlap in such a way as to give us a bonding orbital, right? They're in the same phase, so we're essentially adding these two orbitals in the same phase. We get that sigma 1s bonding orbital. But when we combine those two orbitals, we get the two orbitals out. And so we'll get the bonding and the anti-bonding orbital. And so we'll have also a sigma star 1s orbital. And what we want to do is make sure we can connect these, right, with our lines here. Okay. And so they're connected now, showing the molecular orbitals that come from these pure atomic orbitals. And that'll be more important later on when we do some heteronuclear diatomic molecules. Once we have that constructed, now our molecular orbitals are in the middle. We only have one electron, right, coming from the H atom, not the H plus ion. And so we only have one electron to place in here. Okay. And we're going to come back and look at this from an electron configuration and bond order standpoint in just a minute. Before we do that, we're going to go construct the molecular orbital diagram for H2 minus. Again, these are the same orbitals because we're talking about the 1s orbitals from each hydrogen atom. And so when they combine in phase, or when you add two orbitals together that are the same phase, you get a sigma 1s. If you add them out of phase or subtract them, the same idea, same terminology, is you get a sigma star 1s. And again, we're going to connect those in. Okay. And then, so we've got these now, this sigma star orbital and a sigma orbital coming from the 1s. Now we have 3 electrons because we have a hydrogen atom and an H minus atom for the H2 minus. So we have 3 electrons. We go 1, 2, and 3. So now we have 3 electrons in there, and we've constructed our molecular orbital diagram for H2 minus. The next thing I want to do is go back to the H2 plus, and we're going to put together a molecular electron configuration. And all we do here, when we did an electron configuration for an atom, just any old atom, we took and filled the lowest energy orbitals first, and we filled them from top to bottom, lowest energy to highest energy. And we did so by basically saying, well, we've got our sigma 1s, and I've got 1 electron in there. Hey, that's all we have, right? We only have the 1 electron. That's the only thing we have to depict here, okay? So that's our first electron configuration. For the H2 minus, well, now we have 2 orbitals that have electrons in them, and we have to depict all of them. So we've got our sigma 1s orbital that has 2 electrons, and we've got our sigma star 1s, right, that has 1 electron in it. Right? And so there's our electron configuration for the H2 minus. So it's a similar way of constructing electron configurations, but now we're doing it for a molecule instead of an atom, which means we have to write down the molecular orbitals rather than the pure atomic orbitals that we did back in chapter 7. The other thing we have is the bond order. Right, so on this previous page, we had the bond order. Actually, if we go to the next page, you can see we have this sort of a better picture of the bond order. All right, so here's our bond order picture now, and that, or excuse me, equation. So this equation is a little bit easier to read than the other one, but the idea for bond order, again, we're going to calculate the bond order is the number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals divided by 2. So we're going to come back up here, and we're going to find our bond order for the first one. will equal, well, I have 1 electron in a bonding orbital, 1 electron in that sigma 1s, so it would be 1, minus 0 electrons in any anti-bonding orbitals, so minus 0 divided by 2 equals 1/2. So you can have bond orders that are not integers. They can be 1/2. They can be bigger or smaller than 1, right? It doesn't have to be an integer value. Saying a bond order of 1/2 tells you, in our first comparison will be the bond order of 1/2 for H2 plus to the bond order of 1 that we have down here in the bottom right for H2, which tells you, just based on that bond order, right, the 1 there versus the 1/2 here, it tells you that the H2 plus is going to have a weaker bond than the H2 molecule. Now, if you actually look at the bond order for H2 minus, well, that's going to be 2 electrons in bonding orbitals minus 1 electron in the anti-bonding orbital divided by 2. So that also gives you a bond order of 1/2. Now, the key here, and something we're going to come back to this after we go to the next page here in a second, one of the keys to bond order is when we have a bond order, it's a fairly rough estimate of how strong a bond is going to be. It's not very specific at all. And so there's going to be another piece of information that we want to see to be able to compare these 2 bond orders of 1/2. One of these bonds is going to be stronger than the other, but by a small amount. They're going to be similar in energy, so we're going to have a way of distinguishing which one is going to be stronger. So we'll come back to this page here in a second. The next page, what we have over here on the right-hand side is the molecular orbitals for a helium molecule, He2 helium molecule. So you might think about that in the following way. You could have a helium atom, right, that has a 1s orbital with 2 electrons there, and a helium atom here that would have a 1s orbital with 2 electrons in it, and then in the middle, the He2 molecule. And so if you were to construct this, right, you sort of put it together like so. And I know I did this pretty quickly because the point here is we want to look at the molecular orbitals of helium and look at, in particular, the bond order of helium, which would be 2 electrons in bonding orbitals minus 2 electrons in anti-bonding orbitals divided by 2 equals 0. And so what that tells you, that bond order of 0 predicts that you will not form a bond. In other words, it predicts that this molecule will not exist. And what we have down here in this table 9.1 that we're looking at, so this table here shows you some properties of those molecules we looked at: H2 plus, H2, He2 plus, which this is the same electron configuration as H2 minus, except for different number of protons in the nuclei, and then He2, okay? So if we look at those, we have electron configurations that we can put together for each of them, okay? We've got bond orders. We notice that there are 2 of these that have bond orders that are the same. The bond order of He2, the helium molecule that's diatomic, says it's 0, and it turns out that this whole not observed part, right, this molecule hasn't actually been physically observed in a laboratory setting. And so essentially this idea of the bond order of 0, right, allows us to predict whether a molecule will exist or not. And it turns out that it's a pretty good predictor of whether a molecule will or will not exist. And so in the case of helium-2 molecule, that molecule hasn't actually been observed in a laboratory. So far, so good. Okay. The other thing I told you we'd be able to predict is, well, if we have these molecules with the same bond order, well, we're going to be able to predict which one of them is going to be a stronger bond. And so if you look at the H2 plus or the He2 plus, you'll notice the bond length shows that the H2 plus molecule has a slightly shorter bond length which means that it should have a slightly higher bond energy, right? The shorter the bond, the stronger the bond. Okay, well now bond order in this case is the same, so it's going to be a very different, it's not going to be a very different bond energy, and it's not going to be a very different bond length because the bond orders are the same. Whereas if you compare either of these to the bond order of one molecule, right, that bond order of one shows a much stronger bond, right, almost twice as strong as the bond order of a half. Okay, so what we can do to show that this H2 plus molecule versus the He2 plus or the H2 minus molecule, we can show that those the bond energies should be in this way, such that the bond order of 1/2 for H2 plus is slightly stronger bond than a bond order of H2 plus for He2 plus or H2 minus, because of this one specific property for these particular molecules, and that's this. If you look at the difference in the destabilization of an antibonding orbital, right? So this is what I'm going to depict in green. That magnitude of destabilization for the antibonding orbital is comparable to the amount of destabilization you can get for a bonding orbital. So in other words, from there to there. So the magnitude in blue versus the magnitude in green. Remember, when we have a bond, we have this net stabilization, which allows the bond to form. In other words, that forming a bond causes the molecule to be stable compared to the separated atoms. And so what you'll have in this case is the stabilization that you get, right, for each electron that is in a bonding orbital, right? We're saying that electron is going from a hydrogen atom into a bonding orbital. That gives you some stabilization. That stabilization is going to be less than the destabilization you would get if you put an electron into an antibonding orbital. Thus, if we look at the H2 plus, you get a stabilization of 1 electron, and there is no extra destabilization. If you look at the H2 minus, you get a stabilization of 2 electrons, but then you also have the destabilization of 1 electron that goes to a higher energy orbital. And since that electron that goes to a higher energy orbital is more destabilizing than the one that goes to the lower energy orbital, the overall bond that's formed for the H2 minus is going to be weaker than it is for H2 plus. Essentially, if you consider that the one stabilized electron in H2 plus, right, is similar to having, say, a stabilized electron in H2 minus, except now you have another stabilized electron and a destabilized electron. If the stabilization and destabilization energies were the same, then they would be the same energy bond, but they're not. That extra electron that's destabilized is a higher energy destabilization. And so a way to say this, and you may be able to sort of sort this out, but the idea here is we can sort of keep this in our head as to why the H2 minus molecule might be a weaker molecule. It has to do with the anti-bonding destabilization versus bonding stabilization. And a way to put it is anti-bonding is more anti-bonding than bonding is bonding, right? In other words, the green, this destabilization is a lot bigger than this stabilization there, right? So that's sort of a way, if you want to sort of remember a little way of putting it, that's not a bad way of thinking about it, right? Anti-bonding is more anti-bonding than bonding is bonding, which leads to, even though these molecules have the same bond order, there's more subtlety to it. And so the subtlety leads to the H2 minus having a weaker bond. All right, and so there's hydrogen. Okay, well, hydrogen and helium are all period 1. And so when we go on to period 2, and just a note for you, I don't have all of the sections listed here. Basically, we're doing a bunch of sections together. where we're constructing these diatomic molecular orbital diagrams. And they're also similar. I'm not breaking them up, but we're going to go through them sort of one element at a time until we construct MO diagrams for diatomic molecules of periods 1 and 2, and we complete that, okay? And so the next one we would look at would be the lithium molecule. Now, when we depict the molecular orbitals of diatomic molecules, we're really only going to depict the valence orbitals. Okay, and the reason we're going to do that, we're really interested in the valence orbitals because those are the ones that are going to overlap for bonding. And the other reason is, I can kind of draw it out here, but if you think about the electrons in lithium that are in the 1s orbital, they're core electrons, right? So they're really, 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 really low in energy. They're not going to be involved in bonding, essentially, okay? And so we can look at it from the standpoint of valence orbitals a whole heck of a lot easier than looking at all of the orbitals and all of the electrons in this molecule, okay? So what we're going to do, we're going to draw out our molecular orbital diagram. This is going to be done in a similar way. If we look at the lithium molecule, okay, we're going to make this lithium-2 molecule in the middle, and that's going to be formed from a lithium atom and another lithium atom. If we look at the valence orbitals of the lithium atoms, those are the 2s orbitals. Okay, and if you wanted to know where those 1s orbitals are, right, they're way down lower here, right? They're even probably farther than that down there. So they're so low in energy as to be held really tightly into that nucleus and not be involved in bonding. We're not even going to depict them in our molecular orbital diagram. Just too far off the page for us to care about right now. So here, when those 2s orbitals combine, okay, they're going to combine in such a way that gives us a sigma bonding orbital. This will be a sigma 2s orbital, and then they'll combine in such a way as to give us a sigma star 2s antibonding orbital as well. Right? And so I can connect these together. Notice I didn't even fill in the atomic electrons yet, because really the atomic electrons, we can put those in a minute, but the key here is the orbitals that overlap are what are giving us the molecular orbital diagram. The electrons can come later, okay? Well, each of those lithium atoms is in, so the lithium atom is in the first group of the periodic table. So each of them is going to have one valence electron, which means when you have a molecular orbital diagram, you're going to put the 2 electrons, one valence electron from each of the lithium atoms, into the lower energy of the molecular orbital diagram. And if you wanted to look at the 1s electrons from the lithium, like way down low, so I thought we'd depict these just kind of as a thought experiment, right? Those are down here. You'd be getting a sigma 1s and a sigma star 1s, and you could connect these in, right? And you could fill those in also, right? And you'd have 2 electrons in the bonding and 2 electrons in the anti-bonding orbital there. Those electrons essentially cancel each other out, okay? And so when you have this lithium molecule, you can look at its electron configuration of the molecule as taking into account those electrons, even though you don't really need to depict them. Any molecular orbitals that come from those core electrons are going to cancel each other out. You can still depict them in the electron configuration, and you should, but you don't necessarily need to write them out in the molecular orbital diagram because they're not bonding, right? They're not going to be involved in bonding. So if we were to do the molecular electron configuration, we'd have our sigma 1s electrons that we'll write in, there's 2, and our sigma star 1s electrons, and there's 2 of those, and we just know that they're there even though we don't have to write them because they're sort of in the core, right? And they cancel each other out. Then we can do the ones that are in the valence shell, and so that would be our sigma 2s electrons, and we could put a 2 there. And that's going to be our molecular electron configuration for the lithium molecule. For the bond order, well, we have, and you can look at either your molecular electron configuration or you can look at your molecular orbital diagram. But basically we can see that we have either, and you can take it either way. You can say, if we take it from the molecular orbital diagram, it'll be 2 bonding electrons minus 0 anti-bonding electrons over 2, which will give us a bond order of 1. If we use the electron configuration to do this, right, we've got 2 4 bonding electrons, right, minus 2 anti-bonding electrons over 2 will equal 1, right? 2 minus 2, 4 minus 2 is 2, divided by 2 would be 1. And so either way you do this, you'll get to the same bond order because any of those core electrons are going to just cancel each other out anyway. Okay, and so there's lithium. So this lithium molecule should have a bond order of 1. So it should have a somewhat similar bond to a hydrogen bond. Excuse me, hydrogen-hydrogen bond, which is different from a hydrogen bond in terms of intermolecular forces. Okay, on to beryllium. Beryllium's in the second group. And so our molecular orbital diagram, again, this time we're only going to depict the valence orbitals. So we've got our beryllium 2 molecule. We've got the beryllium atom on the left, a beryllium atom on the right. We're going to look at the valence orbitals. So those are the 2s orbitals still. Each of those have 2 electrons in them. And so when they combine, you have a sigma 2s and a sigma star 2s, and they would combine like so. And then you put in your electrons, 1, 2, 3, 4. So your molecular electron configuration would now be sigma 1s 2, sigma star 1s 2, sigma 2s 2, and sigma star 2s 2. For a bond order, well, based on our molecular orbital diagram, the bond order would be 2 bonding electrons minus 2 anti-bonding electrons divided by 2, which would be 0. It turns out the beryllium 2 molecule doesn't, or hasn't been observed, right? It doesn't exist. Yes, Maya.
Good morning. How do we know how to put the valence electrons in the bonding and the anti-bonding? Is it like 1 for bonding, 1 for anti-bonding? Because you just said 1, 2, 3, 4.
Yeah,
how do
so
we distribute the arrows or the?
So all you're doing, just like when we did an electron configuration for an element, we had the ordering of the orbitals, right? 1s, 2s, 2p, 3s. But now we've got these sigma 2s, sigma star 2s, and the understanding the ordering of those in terms of energies gives you the hierarchy of how we fill them. Now we have the beryllium atom on the left has 2 electrons in it. The beryllium atom on the right also has 2 electrons for a total of 4 electrons.
Okay.
So the beryllium atoms. In the middle is where we have our molecule. Well, the molecule, right, is when those 2 beryllium atoms come together to form a bond, right? And so the valence electrons from the atoms, when they come together to form a bond, will be the electrons in the molecular orbital diagram. So you go from the 2 electrons in each beryllium atom separately to now you put them together. Well, you had 2 beryllium atoms with 2 electrons each for a total of 4 electrons, and we just fill it from the bottom up. And so we
fill the bonding one first, then the anti-bonding?
Always fill the lowest energy first, and then go to the higher energy as you go along. If you have orbitals that are the same energy, right, you go 1, 2, right, then you pair them up 3 and 4, right? Just like we did back in chapter 7 for atoms, only now we're going to put it together as for the molecular orbitals. Okay, so the beryllium 2 molecule has not been seen, right? It's not been observed. When we go on to boron and carbon, the rest of that period 2, what we need to look at now is, well, boron now has 2p orbitals that we need to take into account. So the 2p orbitals of boron, well, I'm gonna draw a little bit of a bigger MO diagram here, try to extend this out so I can depict the 2s and 2p orbitals. And so on the left, we have a boron atom with a 2s orbital and 1, 2, 3 2p orbitals. Well, on the right, we'll have our boron atom, 1, 2, 3 2p orbitals and a 2s orbital. Okay. And in the middle, we're going to have our boron B2 molecule. So one of the keys that we need to know for the overlap of orbitals, when orbitals overlap, they must be oriented with the same symmetry, right? So orbitals, when orbitals overlap, orbitals can only overlap if they have the same orientation or symmetry and there's one other thing here, and that's about their energies, and they must be similar in energy. Okay, so in the case of the boron 2 molecule, you're going to have overlap between the two 2s orbitals to form sigma 2s and sigma star 2s. And remember, these come from orbitals that are, right, spherical in nature, right? So you have 2s and 2s, right, with nuclei there and there. Then you get the 2s bonding orbital, right, something like that, and the 2s anti-bonding orbital, right, it looks something like this, right, where they're out of phase with each other. Same idea as with the 1s orbitals overlapping. And they have symmetry in the case of these sigma bonds along that bonding axis. Now for boron, carbon, and nitrogen, we're going to have a special case where when you look at the p orbitals that overlap, right, you have the px, the py, and the pz, right? And we're going to call the z-axis as our bonding axis. Okay, with that bonding axis, when you have the z orbitals, the pz orbitals overlap versus the px and py. So the pz orbitals are pointing at each other. The px and py are perpendicular to that, right? The px, let's say, is coming in and out of the board at you or in and out of the screen at you. The py would be in the plane of the screen also, right? But they're all perpendicular to the z orbitals. In the case of the overlap of coming from p orbitals, the overlap would be side to side for the px and py orbitals, right? Side to side, because they're going to form pi bonds. And the pz orbitals, right, those are oriented along that bonding axis, and so they would be overlapping in such a way as to be pointing at each other, and so they're going to give you sigma bonds. Now with boron, carbon, and nitrogen, the more stable overlap is going to be the pi overlap that you get from the 2p orbitals, the 2px, say, and the pi 2py. And then those will also have a destabilizing pi star 2px and pi star 2py. Okay. Now, the depiction of these orbitals, we'll actually draw this out for this case so you can start to see this. When you look at the pi bonding orbitals, right, we're talking about having two orbitals if we have two p orbitals that overlap, right? This is sort of what we talked about a little bit earlier, right? If we put these together, we can put them together like that, which leads to well, here's my nuclei, leads to this pi bonding orbital. Okay, so there's my pi bonding orbital. That's right? That's what a pi bonding orbital looks like, where the orbital density, there's overlap in between, right, the atoms, right, above and below the bonding axis. If, however, you have them overlap and they're out of phase with each other, right, like so, when they overlap that way, right, that leads to a pi star or anti-bonding orbital. It looks something more like this. Right, where they have the overall energy of that pi star orbital is higher than you'd get for overlap in the same phase. And so that's what these, so this would be a pi star orbital up there. The other way to overlap orbitals is if you have the PZ orbitals. And the PZ orbitals, right, those are oriented along that bonding axis. So they're like this, right? And if they're in phase with each other, right, when you add those ones together, well, here's my two nuclei, you get a big old bonding, right, overlap in the same phase, right, and some small little lobes that are out of phase, and you get this overall net sigma bonding orbital that's coming from a 2p. So that would be your sigma 2pz. Okay, but you can also add them together such that they're out of phase with each other. Right, where you'd have that destructive overlap. And in that case, you would get something more like this, which would be a sigma star orbital. That would be your sigma star. And that sigma star would be the highest energy in orbital. And it would be the highest energy orbital. It's the sigma star 2pz. It's the highest energy orbital because the orientation of those two orbitals is towards each other. And since they're oriented towards each other and they're out of phase, that's a lot of destabilization. It's basically a really good overlap to destabilize these orbitals. And so they're going to be a net repulsion overall. And so for boron, carbon, and nitrogen, the ordering is going to be such that you have the 2s, the sigma 2s, the sigma star 2s, the two pi 2p orbitals, pi 2px and pi 2py, the sigma 2p orbital, then the pi star orbitals and the sigma or star orbitals up top. Okay, and that's going to be the ordering there. Now, in each boron atom, we have a total of 3 valence electrons. So 1, 2, 3 valence electrons. And so we have a total of 6 valence electrons that are going to be involved in the bonding here. And so you would go 1, 2, 3, 4, 5, 6. I missed something here. I was not paying attention to where my sigma star orbital is. So let me go back here. I'm gonna put those electrons back in. Hard to read my own writing, apparently. 1, 2, 3, 4, 5, 6. That makes more sense. Okay, and so you'd fill those electrons in. You could do a molecular electron configuration. Right? Sigma 1s, even though we don't depict them, they're still there. Sigma star 1s, 2, sigma 2s, 2, sigma star 2s, 2. Then you would have sigma 2p, 2. So there's our molecular electron configuration. With a bond order of, in this case, we can see there's 1, 2, 3, 4 electrons in bonding orbitals, right? 2 of them are in the sigma 2s, and 2 of them are in the sigma star 2s in our molecular orbital diagram. So 4 minus 2, we've got 2 electrons in the sigma star 2s, divided by 2 gives you a bond order of 1. And this has been seen to exist. There's going to be more about this one in just a second as well. Okay, but that's your MO diagram for the boron molecule, B2. We can also do it for carbon. For carbon, we got our 2s and 2p orbitals. And you can see that sometimes I'm filling up the electrons early, like right at the start. Sometimes I wait till the end. It doesn't really matter what order you do it, as long as your final MO diagram comes out right. So you got a carbon atom on the left, a carbon atom on the right, and a C2 molecule in the middle. Each carbon should have 4 valence electrons. So 1, 2, 3, 4. 1, 2, 3, 4. Okay, so our sigma 2s orbital will come from the overlap of the 2s orbitals of the carbon, and a sigma star 2s orbital will come from that overlap as well. We'll connect those in. Okay. And then we're going to have our overlap of the p orbitals. And again, the ordering is the same. We'll have our pi 2px, pi 2py, followed by our sigma 2pz. I'm not expecting you to draw these perfectly in to scale. That's just not something that I expect. I just want you to have them in the right order. So we've got our pi star orbitals come next. Pi star 2px, pi star 2py, and then way up top we have our sigma star 2pz. And we connect all these in. Okay. And then the next thing we would do is go and fill in the electrons. So we've got 4 electrons from each carbon atom, which gives us a total of 8 electrons, and we'll start filling from the bottom. So 1, 2, 3, 4, 5, 6, 7, 8. For a molecular electron configuration of sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2p. Now we're going to group all of our, oh, what did I miss something on? I need to go back and change something on the boron one. I just realized that. So the pi 2p, we're going to have 4 electrons in the pi 2p orbitals. Detour back to where we were at. I made a mistake over here as I was going through this. These should be the pi 2p orbitals with 2 electrons in them, right? That's these ones right there. Sorry about that, guys. Hopefully I'll give you a chance to go and make note of that. But and so with the carbon molecule, right, the C2 molecule, you have your 1s, sigma 1s and sigma star 1s are filled, your sigma 2s and sigma star 2s are filled. Now your pi 2p orbitals are also filled. And we can calculate the bond order, which has 2, 4, 6 bonding electrons minus the 2 anti-bonding electrons in the sigma star 2s divided by 2 will give us a bond order of 2. And so this molecule, the C2 molecule, has been shown to exist with a bond order of 2. Okay. All right. So we've got N2 versus O2, and this is where we're going to see as we construct these MO diagrams, we're going to have a change in how we order the orbitals of the bonding pi orbitals and the bonding p sigma orbitals from the p orbitals. Okay, so with nitrogen, it's going to be the same as what we've done so far. So we've got our 2s and our 2p for one nitrogen. The other nitrogen has its same orbitals, 2p, 2s. Okay. When they form the N2 molecule, the 2s orbitals overlap to give you a sigma 2s and a sigma star 2s. When the p orbitals overlap, you still get the pi 2px and pi 2py and the sigma 2pz in that same order. And the pi star 2px, pi star 2py, and the sigma star, the sigma star 2pz. And we connect them all in the same way. Okay. Nitrogen, so each nitrogen should have 5 valence electrons, so we can fill those in now. Okay, which means we should have a total of 10 valence electrons to fill in our molecular orbitals. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And we can construct our molecular orbital or molecular electron configuration: sigma 1s2, sigma 1s star 2, sigma 2s 2, sigma star 2s 2, pi 2p 4, and pi star 2. Excuse me, not pi star, sigma. Sigma 2p. Hey. Sigma 2p 2. This will give us a bond order of, well, I've got 2, 4, 6, 8 electrons in bonding orbitals minus 2 electrons in anti-bonding orbitals divided by 2 gives us a bond order of 3. Okay. All right. So something else to compare this to, if you think back to doing Lewis structures back in chapter 8 stuff, right? The Lewis structure for a nitrogen molecule, if you remember the end of that Lewis structure lab, you looked at N2 as a molecule and you saw, oh, hey, the N2 bond order is a 3 here, right? Well, that's actually depicted in the Lewis structures for some of these. Okay, and sometimes it's depicted well and sometimes it's not depicted well. In fact, for oxygen, it's not as well as we would like. Okay, so there's our nitrogen molecule. It's triple bond. It's got a bond order of 3. It's a pretty strong bond. The oxygen molecule is going to have one key difference. We're going to set it up the same way. It's when we construct our molecular orbitals that we're going to have it different. So let's put together our oxygen atoms. 2s and 2p. Actually, move my 2p orbitals up a little higher for just space sake. All right, so there's my other oxygen atom. In the middle, we'll have our O2 molecule. Before we do that, I'll fill in the electrons on the oxygen molecule. So there should be 6 valence electrons on each oxygen. Okay. So we construct these initially in the same way. The sigma 2s and sigma star 2s are still formed in the same way that they were on nitrogen. So sigma 2s, sigma star 2s. Okay. Now the big change here is when we go to oxygen, the big change is, and I'll try to illustrate this on here, right? So what happens is you wind up having the sigma 2pz orbital goes lower in energy, and the pi 2p orbitals go higher, okay? And so they flip, okay? And there's a reason that they flip, and I'll talk about that in a minute. But the ordering switches. So now the next orbital that you should have is the sigma 2pz, followed by the pair of pi 2px and pi 2py orbitals. Okay. And the orbitals up top stay in the same order. So they're going to be still pi star 2px and pi star 2py will be in the same order as they were for nitrogen. So those are going to stay the same, and the sigma star will be the highest energy. So the only orbitals that flip are the ones in the middle there, okay? And then we'll connect all of them in. And so the reason that these orbitals are in a different orientation, basically every single element, if you were to do the MO diagram for every element from oxygen on, okay, will have this same ordering that oxygen does. The reason it's different for boron, carbon, and nitrogen, and in the case of beryllium and lithium also, if you were to look at the orbital simulations, has to do with this thing called sp mixing, which is due to largely the size of the s and the p orbitals of those elements that are smaller atomic number than oxygen, but of course larger sizes than oxygen. And so this is just the case for anything from lithium through nitrogen, and we really only see it for the most part when we're really looking at boron, carbon, and nitrogen, because they're the ones that have p orbitals that are going to overlap and be filled with electrons. And so we're going to look at sort of the relative ordering of all of these orbitals in just a minute, but there's some other things that we needed to look at before we get there, okay? So we're going to finish up the MO diagram by filling in the electrons. We've got a total of 6 electrons on each oxygen, so when they come together to form the O2 molecule, that's 12 valence electrons to fill in. So we fill in 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Notice we have to put some electrons up here in the sigma star orbital, so 11 and 12, okay? Now, that will give us a molecular electron configuration of sigma 1s2, sigma star 1s2, sigma 2p2, sigma star 2p2. But remember, we're putting these in order of the lowest energy, so our next orbital is the sigma 2p orbital. The sigma 2pz has 2 electrons. Then the pi 2p has 4 orbitals, have 4 electrons. Then we have our pi star orbital. Come on. And my pen is slowing down now. Okay, so we'll have our pi star 2p, and there are going to be 2 electrons in there. Now this will give us a bond order of, well, we've got 2, 4, 6, so 2, 4, 6, 8 bonding electrons, minus 2, 3, 4 anti-bonding electrons, over 2, which will give us a bond order of 2. And this agrees well with our Lewis structure for an oxygen molecule. However, there's something that doesn't agree well in our Lewis structure. And the thing that doesn't agree well in the Lewis structure is what I'm going to direct you to, this whole thing down at the bottom, this diamagnetic versus paramagnetic. Okay. Diamagnetic is going to tell you tell you about the magnetism of a compound. So diamagnetic says that a compound has no unpaired electrons. Okay. Oh, did I miss the, there was a question about a sigma 2s. One second. Did I miss my sigma? Oh, I did miss my sigma 2. What did I do? I missed my sigma 2s because they are there. I just wrote them as 2p. They should be sigma 2s. These ones down here. That and that. Thank you for pointing that out. Sigma 2s and sigma star 2s. All right. Sorry about that. Okay. Come on. So thanks, Jessica, for pointing that one out. Okay. So what we have here is if you have a diamagnetic substance, it could be an element or a molecule. If there are no unpaired electrons, it means it's diamagnetic. And if there are paired electrons, so excuse me, if it has any unpaired electrons, I should say. Come on. Okay, if it has any unpaired electrons, it's considered paramagnetic, and basically it shows that it's attracted to a magnetic field, or pulled into a magnetic field. And so essentially this is the thing that's paramagnetic, has these unpaired electrons that interact with magnetic fields. They're attracted to magnetic fields because of the unpaired electrons, because those little magnetic fields from the electron spinning can now interact with the magnetic field that they come in contact with and be pulled towards it. So it interacts with that magnetic field. And so in other words, another way to put it is it shows magnetic properties. So an example would be iron as an element has a bunch of unpaired electrons. That's why iron is something that is attracted to magnets, right? Iron itself isn't necessarily magnetic, but when it's in a magnetic field, all of those electrons essentially align with the magnetic field to be attracted to it and interact with that field. And so with oxygen has 2 unpaired electrons, right? So it is paramagnetic. Whereas nitrogen is diamagnetic. So oxygen actually does interact with a magnetic field. If you were to take oxygen, say liquid oxygen, which would have to be very, very cold, and you don't really want to concentrate oxygen because it's dangerous, but if you were to take that and just drizzle a stream of liquid oxygen and put a magnetic field into it, it would interact with that magnetic field. If you were to say put a magnet near it, it would be pulled towards that magnet. It's kind of an interesting thing, but it does happen. Now, the Lewis structure, right, doesn't show that, right? right? Because remember that Lewis structure is really showing things based on, showing molecules based on the localized electron bonding model. So it's not showing the magnetic and electronic properties of the molecules. So if we were to go back up and look at boron and carbon, notice boron would be, right? It's got 2 unpaired electrons, right? And so that would be paramagnetic. Whereas carbon, right, would be diamagnetic. Okay. All right. Carbon, boron, we've done nitrogen, oxygen. So we've got 2 more of these in this first row, or the second row of the periodic table. So we can finish our first 2 rows. We can do that with fluorine and neon. So we'll have 2 fluorine atoms, 2 s orbitals, and 2 p valence orbitals. Another fluorine atom. Each of those will have 7 valence electrons. And then we'll have our F2 molecule in the middle. Again, the 2 s orbitals will combine to give us sigma 2s, sigma star 2s, our lower energy orbitals from the overlap of the p orbitals will be the sigma 2pz, followed by the pi 2px and pi 2py. Next will come our pi star 2px and our pi star 2py, followed by our sigma star 2pz. Okay. And we've got 14 electrons to fill in, 7 from each fluorine, so we can fill from the bottom up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we start to fill our pi star electrons, 11, 12, 13, 14. And so our molecular electron configuration would be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2p2, pi 2p4, and pi star 2p4. For a bond order of, well, I've got 2, 4, 6, 8 bonding electrons minus 2, 4, 6 anti-bonding electrons. So for a bond order of 1. And that does agree well again with that Lewis structure. So the Lewis structure of fluorine should look something like this. And something you can kind of look at here is there are 6 lone pairs of electrons on the fluorine molecule for a total of 12 lone pair electrons. And so if you look at the total number of electrons here, right? You've got the 1s and the 1s star, the sigma 1s and sigma star 1s orbitals, the sigma 2s and sigma star 2s orbitals, right? That gives you a total of 8 electrons plus the pi 2p orbitals give you another set of excuse me, I'm got my thing mixed up. My sigma 2s and sigma star 2s electrons gives me 4 electrons that aren't going to really be involved in bonding because they cancel each other out. And we've got the, I'm having an issue on here. Well, let's put it this way. What I'm trying to illustrate here is that the bond order, while the bond order gives you a good estimate of the bond strength, and the Lewis structure can have the same bond order based on the number of bonds here, the electrons that are depicted in the Lewis structure aren't really explained as to which orbitals they're coming from. Okay, that's sort of what I was trying to get at in a rough way right there. Okay, finally, the last of the molecules, of the diatomic molecules and those predictions for periods 1 and 2 is neon. Now, each neon atom will have 2s and 2p orbitals. And there will be 8 electrons in the valence shell of each neon. When we combine the orbitals, they're going to combine in the same way that fluorine and oxygen did, because every element after oxygen, or oxygen and beyond, has that same ordering of those sigma 2p and pi 2p orbitals. So here we're going to have the sigma 2s and sigma star 2s. We're going to have our sigma 2pz followed by our pi 2px, pi 2py, pi star 2px, and pi star 2py, and then our sigma star 2pz for the Ne2 molecule. And we're going to connect those all in. Okay, with a total of 16 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. With the molecular electron configuration, sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2p 2, pi 2p 4, pi star 2p 4, and sigma star 2p 2. The bond order, well, we've got 2, 4, 6, 8 electrons in bonding orbitals, minus 2, 4, 6, 8 electrons in anti-bonding orbitals, over 2 equals 0, and it turns out that neon in E2 has not been observed. Okay, we have now constructed MO diagrams for all of the elements, homonuclear diatomic elements in the first 2 rows of the periodic table. And we've used that to predict whether these exist. And it turns out that the ones that have a bond order that's non-zero have been shown to exist, and ones that have a bond order of 0 have been shown not to exist. We also looked at the orbital orderings of the elements, each of these elements where their orbitals sort of shift when you go from nitrogen to oxygen, right? So the nitrogen sigma 2pz is higher in energy than the pi 2pz orbitals, right? And so what happens there, right? That's when you go between oxygen and nitrogen, right? There's the shift, and a way to look at it is the shift as you move from right to left is such that when you get to nitrogen, there's this thing called sp mixing that happens that causes, now you can see it all sort of in, relative to each other, it causes the sigma 2p orbitals to be higher and higher in energy as those atoms get larger and larger in that second row. And so that's where it switches, right? Every element beyond oxygen, or oxygen and beyond, will have the ordering where the sigma 2pz orbitals will be lower in energy than the pi 2p orbitals, okay? And so if we look at all of the electron configurations of all these from lithium on to neon, so Be2, so this one has been shown to exist, but you can see that this bond order is so small, right? That's something that has existed in a laboratory for a very short time. That does not take much energy to break that bond. So that's almost, so I guess this one has been observed, but it's not going to be observed for very long because it's going to want to break apart very quickly. There's not much stabilization to keep that together. Whereas if you look at the neon molecule, right, that neon molecule has not actually been observed in a laboratory at all. Right? If you look at the bond energies of, let's say compare boron, right, had a bond order of 1, has a bond energy of, so 0.493 attojoules, which is 10 to the minus 18 joules. That's for one bond, right? To carbon, which had a bond order of 2. In this case, it's more than double. To nitrogen, which had a bond order of 3, right, which is triple the bond order of the boron. And then oxygen, which has a bond order of 2, has a bond order that's about 2/3 the order of nitrogen, a little bit less than that in the case of oxygen. But part of the reason for oxygen having a bond order that's less than 2/3, that's less than carbon, is because oxygen has those electrons in the antibonding orbitals. And on top of that, you've got these unpaired electrons there as well, which give oxygen magnetic properties, whereas nitrogen doesn't have those. And so what we'll do here is we're going to stop there for the day, and we're going to pick up with heteronuclear diatomics next time around. As you can see, we'll do a few of those, and then we're going to start to look at how the localized electron bonding model and the which utilizes hybrid orbital theory and the molecular orbital theory, sort of how they come together. And we'll also learn a new way of drawing molecules that'll be important to you in many, many places in the future, which I'd like to introduce here sort of at the end of this chapter so we can more easily draw certain molecules and we can more easily pick out the types of orbitals that are involved in the bonds. So I know that was a lot of molecular orbital diagrams. I do that for one lecture every term just to beat molecular orbitals into your heads. It's a lot, but hopefully you've seen enough molecular orbital diagrams to see how they go, and you can get practice doing those same ones. What I will tell you is I will only have you do molecular orbital diagrams for diatomic molecules. I'm never going to have you do molecular orbital diagrams for anything beyond diatomics, at least for our class, okay? And so with that, I'll stop recording in today's lecture and see if there are any other questions here.